Good day to everyone. Welcome back to my classes. Today, seventh lesson of moving charges and magnetism. Class 12, chapter 4. Okay. In the previous lesson, we have learned Ampere's circuital law and its application. We derived the equation for the magnetic field due to a straight wire carrying current. Today we will discuss magnetic field due to a solenoid, and we apply Ampere's circuital law to derive the magnetic field inside the solenoid. Okay, and you know Ampere's circuital law. Once again, I will state for you. Ampere's circuital law states that the line integral of magnetic field around a closed loop is equal to mu0 times the current enclosed by that loop. That loop is known as Amperian loop. At every point on the Amperian loop, B is constant and B is tangential to the length. Okay. Now we will discuss magnetic field inside a solenoid. What is a solenoid? In 10th standard, you all learned solenoid. It is a wire wound in the form of a helix. Okay, take a wire wound in the form of a helix. So a solenoid has large number of circular turns. We are wounding in the form of circle. Okay. It is a helix. So a solenoid has large number of closely wound turns. And we will discuss a long solenoid. Long solenoid means its length will be more large compared to its radius. And magnetic field due to a solenoid is similar to that of a bar magnet. You know the magnetic field pattern due to a bar magnet. So the field lines exactly same as that for solenoid also. Magnetic field lines pattern for solenoid and bar magnet are the same. Okay, so we will continue the derivation and we find the magnetic field applying Ampere's circuital law. Magnetic field due to a long solenoid. Long solenoid means length of the solenoid is very large compared to the radius. A solenoid consists of large number of turns. The turns are very close to each other. I will give a diagram of the solenoid. So the magnetic field pattern is shown in the diagram. See the turns, circular each turns. Okay. I just represent the current and just marking the current through each turn. See the left turn, current is downward like this. This is the direction of current through each turn. Okay. Magnetic field patterns, you look at the top part of the turns. Their current is coming out of the plane of the paper. That is why the dot is shown. Okay, so that top small part of each turn is straight. So there, that magnetic field due to circular, that straight conductor is shown in the form of circles. You can see that around each wire, concentric circles represents the magnetic field line. And when you see between two turns, see the point, I just mark it with a blue dot here, between at this point, see the green dot, magnetic field due to two turns are opposite. So the field cancel between the turns. Remember this. Okay. And you see at the center field is maximum. Center of the solenoid field is maximum. Now let us apply Ampere's circuital law and calculate the magnetic field due to the solenoid. So you see the top part of the solenoid, through each circular turn, current is coming out of the plane of the paper. That is why they have marked dots there. And lower part, you can see current is moving into the plane of the paper. That is why they are represented by into mark. Okay. And I am drawing the top and bottom part separately. See, this is the top part of the solenoid. You can see many turns like this. You can see all currents are coming out of the plane of the paper. So I just mark dots there. This red dots represents currents moving out of the plane of the paper. Okay. Now I am drawing the lower portion of the solenoid. See lower that cross section of the solenoid, lower portion. Okay. Here you know the turns, currents are moving into the plane of the paper. So I represent by into mark there. Okay. Here current is into. Current is moving into the plane of the paper. Since we are considering a very long solenoid, the magnetic field lines will be constant along the center, like this, uniform magnetic field. Okay, this is a portion of the infinitely long solenoid. Magnetic field lines are straight and parallel, uniform. Now to apply Ampere's circuital law, you need a loop called Ambient loop. So I am considering an Ambient loop, okay, a rectangle. I am considering a rectangular loop. Okay, that is one side of that loop passing through the middle of the solenoid. See, this is the ambient loop I am considering. This rectangle. So I am naming it A, B, C, D. Okay. See, the side AB is through the center of the solenoid. Okay. Now I am going to apply Ampere's circuital law. What is the equation for Ampere's circuital law? Closed integral B dot dl. Okay. And I am taking integral over that rectangular loop. So I am taking it as A, B, C, D, A. This is the rectangular loop. Equals mu 0 times I. Okay. Now you can split the integral into 4 parts. AB is a part. Okay. CD is another part of the loop. DC and DA. So I split it into 4 parts. Closed integral A to B. You integrate along A to B, B dot dl plus closed integral integral. Now don't write the closed integral because we are splitting. Okay, so integral a to b dot dl plus integral b to c b dot dl integral b to c b dot dl plus integral c to d b dot dl plus integral d to a b dot dl is equal to mu 0 times I. Okay. Now you can see that along the length AB, magnetic field is like this, parallel to the axis direction. Length AB also parallel. So cos theta will be 0 here. Theta will be 0. So you can write A to B, B dl cos 0 plus integral B to C, B dl. See, over the portion BC, magnetic field is towards this right? But length is perpendicular to that theta 90 degree. So B dl cos 90 plus closed integral C to D, B dl. There also magnetic field and DL are anti-parallel, but that length DC is very far away from the center, so that integral I am neglecting. So integral C to D, BDL cos 180 I am neglecting. Why we are neglecting it? We can take it as 0 because the part CD is far away from the center. Part CD is far away from the center. Okay. Then you consider the part D to A. Integral D to A BDL. See, for the length AD, magnetic field is towards right. Length is in this way, DL, right? They are perpendicular. So cos 90. Okay. Cos 90. This is equal to mu 0 times I. Now, A to B, BDL, cos 0 is 0. Sorry, cos 0 is 1. So BDL plus the second term, B to C cos 9, BDL cos 90 is 0. Third term is negligible. We are neglecting 0. Fourth term also cos 90 is 0. So it is mu 0 I. Okay. Then what will be the remaining? Closed integral A to B, B dl is equal to mu 0 I. And what is this I? I is the total current circulating through the solenoid. Okay. So you can see that through each turn, current coming into the solenoid is I only. Okay. So each dot represents I for the lower part, for the upper part. Okay. So each circular turn, for the top part, you see each circular turn, one dot is represented, that is current coming out. If n is the number of turns per unit length, so for each turn, current I is coming out. If N is the number of turns per unit length. What will be the total current coming out? For each turn, I current comes out, right? So in a length L, how many turns are there? N into L. So N, small n is the number of turns per unit length. So in a length L, what will be the number of turns L in a length L? So we can find out the total current enclosed by the rectangular loop. Total current enclosed by that rectangular loop. That is ambient loop is, current coming out through unit length is N. In that length L, how many turns will be there? N into L, right? N is the number of turn per unit length. So in the length L, what is the total number of turns? Small n into L. Okay, where L is the length of the solenoid. So we can write V into integral A to B dl equals mu 0 into total current enclosed is N into L into I. Current through one turn is I. Current through NL turn is NLI, because N is the number of turns per unit length. You see how many dots are there in that rectangular loop? N into L. Through each dot means one current. Each turn gives one I current. So that AB length gives NL into I current. Okay, current through one turn is I. So current through NL turn is NL into I. So we can write the equation mu 0 N L I. And integral A to B dl is L only, length of the solenoid. So we can write BL equals mu 0 N L I. You can cancel this L. So we got the equation for magnetic field inside the solenoid. V equals mu 0 N I. This is the magnetic field at the center of the solenoid. Okay. Okay. At the solenoid, magnetic field at the center of the solenoid is mu 0 Ni. Outside the solenoid, it is 0. What is N here? Number of turns per unit length. Okay. I is the current. So this topic is very important. We applied Ampere's circuital law to find the magnetic field inside a solenoid. Magnetic field outside the solenoid is 0. Magnetic field at the center is mu 0 Ni. Okay. So magnetic field of a solenoid, magnetic field pattern resemble like a bar magnet. Now, the third application of Ampere's circuital law, we are going to find out magnetic field inside a toroid. What is a toroid? You take a circular ring, wind large number of turns of a wire. So you take a circular ring, take a long wire and wound number of turns over it. It looks circular. It looks as if a solenoid is bent into the form of a circular loop. Okay, you take a long solenoid, you bend the solenoid into a circular loop, then you will get a toroid. Okay, now we will find out the magnetic field inside a toroid by applying Ampere's circuital law. So you take a ring, non-metallic ring, right? This is a non-metallic ring. Take a wire wound over this like this. Wind the number turns like this. Or it can be considered as a solenoid bent into the form of a circular ring, a circular loop. So this is a toroid. Okay. And we are going to find out the magnetic field due to this toroid. You can find out magnetic field outside in the outer region, exterior region, this region. And we can find out the magnetic field in the open space in the middle of the toroid. And we will find the magnetic field inside that ring. Okay. So we have to consider three regions. One is exterior region, I name as Q. One is inside the open space, I write as this point P. And one more point I will consider in the interior of the ring. Yes. Okay. So you need to consider 3 Ambient loop. To find out the magnetic field at these 3 points, we need to consider 3 Ambient loop. Okay. First, magnetic field in the open space of the solenoid. Magnetic field in the open space in the middle of the toroid. So you imagine, you consider the open space, a point in the open space P. So you need to draw an ambient loop. And drawing an ambient loop surrounding the point P. See, this is an ambient loop, this red circle. But you know, this circle is not enclosing any current. Current is not flowing through this. Okay. You can see that current is flowing through the circular turns only. There is no current inside the ambient loop 1. I name as this ambient loop 1. Okay. So consider ambient loop 1. Okay. What is the formula? Closed integral B dot dl is equal to mu 0 I. But this loop does not enclose any current. So magnetic field is 0. So magnetic field in the empty space of the empty space enclosed by the toroid is 0. Okay. Now we have to find out the magnetic field in the interior of the solenoid. So you need another ambient loop. Okay. And considering ambient loop 2 in the center, right? This one. You consider the point in the interior midpoint of that ring. This is ambient loop 2. And you can see that this loop encloses, when you consider that turns, current is entering. Okay. You can see that current is here at the lower portion of the ring, current is coming out. Here current will be coming out. Okay. And at the top of each turn, current will be moving into. It always like that. I am taking current moving, top part moving into. So according to the diagram, and writing 1 minute. Lower portion of each turn. You consider lower point of each turn. The current is moving into the plane of the paper. Okay, current is moving into the plane of the paper. So that I represented by into mark like this. For each turn at the lower part of that ring, current is moving into the plane of the paper. Right? And for the outer part of each turn, current will be then coming out. We can represent by dot. Okay. Like this dot. And just drawing randomly some only. Okay. So, you know, each turn current is circulating like this, right? So from the top part of each turn, current comes out. Lower part current each move into the plane of the paper. Okay, and you can see that this black loop, loop 2, ambient loop 2, encloses only current moving into the plane of the paper. And how many currents are moving into the plane of the paper? N into L into I. Because length is L. Okay. Number of turns per unit length is small n. We consider number of turns per unit length is small n. So what is the total number of turns passing through the entire circumference of that ambient loop 2? 2 pi r into n. So total current is circulating. Total current enclosed by ambient loop is 2 pi r n into I. Okay. So keep this in mind. So now we are considering ambient loop 2. Consider ambient loop 2. Ambient loop 2. Okay. What is the equation? Closed integral v dot dl equals mu 0 times I. V dl is equal to mu 0 times I. What is I here? I told you I is the current through each turn. So, you know, the ambient loop, second loop contain many currents moving into the plane of the paper. What is the total number of currents moving into the plane of the paper? N into length into I. N is the number of turns per unit length. Length is the circumference. I is the current through one turn. So what is the total current enclosed by the ambient loop 2? N into 2 pi r. What is n? Small n, number of turns per unit length into I. I is current through each turn. Okay, current through each turn. And if you integrate dl, you get circumference only. Total length of the loop is what? Circumference. Mu 0 n 2 pi r I. So you can cancel 2 pi r. So B will be what? Mu 0 n I. So what is the magnetic field in the interior region of the toroid? Interior region means inside that ring. Okay. So magnetic field in the interior of the toroid is 0. Is not 0, you got it. B equals mu 0 Ni. It is same as that of the solenoid. Now you can find out the magnetic field in the exterior point. See the point Q I marked there. So for that you need another ambient loop. Okay, that is passing through that point Q. So I am drawing another ambient loop. See, this is the loop 3. Okay, loop 3. You see this big loop encloses currents moving into the plane of the paper and currents moving out of the plane of the paper. You know, over the top part of the that turns of the toroid, current will come out. Over the lower portion of the turns of the turns of the toroid, current moves into the plane. Both are equal. Currents are equal and opposite. So net current will be 0. Okay. So third loop also does not enclose the current. Now you have to consider the ambient loop 3. Ambient loop 3. Okay. Here net current is 0. Why net current is 0? This bigger circle, that bigger ambient loop encloses currents coming out of the solenoid and currents moving into the plane of the solenoid. Both are equal and opposite. You know, for circular turns, for each turn, top part current comes out of the plane of the paper in the diagram. And through lower part of each turn, same current moving into the plane of the paper. So these currents are opposite, equal in magnitude. So net current is 0. So what is the reason? So the magnetic field is 0. So magnetic field in the outside region also 0. Okay. What is the reason for this? Net current is 0. Sum of currents moving into the plane of the paper. Equals sum of currents moving out of the plane of the paper. Therefore, net enclosed by the ambient loop, net current enclosed by the ambient loop is 0. Therefore, net current enclosed by the ambient loop is 0. So at the exterior point also magnetic field is 0. So for a toroid, magnetic field in the open space, okay, is 0. Magnetic field in the exterior of the toroid, outside the toroid is 0. And there is magnetic field only in the interior of the ring. That is given by mu0 Ni. Okay, children? Now I end this class. Thank you for watching. Watch video again. Make your concept stronger. Okay? Improve in your physics. Get full marks. We will meet in the next class. Goodbye.